Remember that we also defined something called the cutset rank, which was just a fancy name for the number of edges in a spanning tree of a graph. Now let's look at a similar construction as we did for cycles, namely fundamental sets of cutsets, to get a better idea of the relationship between spanning trees and cutsets. So again, the setup is you have a connected graph G, and in it you have a spanning tree T. Now, instead of adding edges, we remove edges. So remember, in a tree, one of these many properties trees have is that each edge you remove will disconnect the tree. So if you have, let's again draw an example. So we have, say, this graph and the blue spanning tree. I'm taking a different blue spanning tree each time. Let's say this one, doesn't matter. So now if I remove an edge, say remove this edge, then I will have disconnected my spanning tree into two parts, this single vertex and the rest of the spanning tree. So these are my components H and K in my tree. And so the set of all edges that go between H and K is a cutset in G. It's a separating set because, so again, if I look at what I just drew earlier, so these edges in dots, this is a cutset. Why is that? Well, because if I removing it disconnects the graph, and if I remove any subset of it, so if I leave one of these edges, then I will have a tree because I have just the required number of edges and no cycles. So it will be a tree, it will have to be connected. So such a cutset is somehow the cutset associated to this edge. And the set of all cutsets that are obtained in this way are called a fundamental set of cutsets associated to our graph, associated to our tree T. So this is a bit more complicated than with fundamental sets of cycles, but let's look at an example to see what it actually looks like. So let me take as my G the same graph that we always use in this business. So this graph, and let me take as a spanning tree, well, let's be boring and take the same spanning tree we usually take. Okay. So now I am going to remove one edge from T. And I can do this in three ways. Obviously, since there are three edges that I can remove from T, because T has three edges. So let's start with this edge. This edge is called E. If I remove E from T, I will get a graph that looks like this. So now my components consists of this vertex of G and this part of G. So now my cutset will be whichever edges in G connect these two components. So one of them is the edge E, but there's this other edge, let's call it F, that I also need to remove. I have no choice. If I want to disconnect the graph, if that's my mission in life, I have to remove this edge together with E to get a graph G disconnected in the way indicated by my disconnected forest here. So if I take G and I take EF, then the graph will look like this, and it's disconnected. So EF is one such cutset. Okay, that's what we did with the edge E. Let's do the same thing with the edge E prime. So if I take t minus E prime, then I will get something that looks like this. So I need to remove E prime from G, but also this edge, let's call it F prime. And indeed, if I do that, I will get a graph that looks like this. And finally, I can remove this edge, which I will call E bis, or double prime, as some people say. What do I get? Then I get something that looks like this. And so to separate in the graph G, now I want to separate this vertex from the rest of the graph. Then I have to remove 4 edges. So I have to remove, well, E bis, but also F bis, which is this one. It's getting a bit messy, but I have to remove this lower bow, so to speak, the upper bow, which was E bis, but also F and F prime. This is a cut set, and so I have to remove it, and if I do, I will end up with a graph that looks like this, which happens to be exactly what the tree looks like. So now our fundamental set of cut sets consists of this cut set, and this cut set. So all 3 of them together. This is the fundamental set of cut sets. So it consists of 3 cut sets: EF, E prime, F prime, and E bis, F bis, F, F prime. So the philosophy here is that I take an edge away from the tree. This defines uniquely a subdivision of the tree into 2 components. And this in turn defines uniquely a cut set from G that I would have to remove to get the corresponding subdivision of G. So the edge defines the cut set. So I will get one edge, one cut set for each edge that I had in my tree. And each tree gives me such a fundamental set. And the number of edges in the tree, this was what we called the cutset rank. So I made a mistake here. It's cutsets. So any fundamental set has this number of cutsets because this is the same number of edges as the tree has, and any edge determines a cutset completely. So in our example, our fundamental set of cutsets consisted of EF, E prime, F prime, and E bis, F bis, F, F prime. So it had 1, 2, 3 cutsets. And so this is why the cutset rank is called the cutset rank. It is the number of cutsets in any fundamental set of cutsets. The whole thing is analogous to that of fundamental cycles. And if you have the time and energy, you can read up on matroid theory, or what we will have time to cover, duality of graphs, and then you will see how the concepts of cutsets and cycles have a fundamental duality relation between them. But more on that later.